In this video, we will practice taking the derivative when y is not by itself. We will also practice taking the derivative with respect to other variables besides just x. This is called implicit differentiation. If you appreciate the content, please give it a like. This is the graph of this equation. Let's find the equation of the line tangent to the graph at 2, -1. We always write the equation of a tangent line in point-slope form, so we need a point and the slope. They already gave us the point of tangency, 2, -1. So we just need to find the slope. In calculus, the slope is given by the derivative, so we need to find dy dx. We begin by taking the derivative of both sides of this equation with respect to x. Let's go term by term. I encourage you to always think in terms of the chain rule. So if we take the derivative of the outer function, this will be 2x. But then if we multiply by the derivative of the inner function, which is just x, we are multiplying by dx dx, which of course cancels out. So I know that felt a little silly because, the derivative of x squared is just 2x. But a common mistake is that students will forget to do the chain rule when they need to. So if you kind of do the chain rule every time, if it cancels out, it just cancels out. But if you do it every time, you won't forget it. On the next term, we are going to need the product rule. I need you to be very intentional about how you handle this negative sign. I encourage you to include the negative sign with the first factor, the first function. So I'm going to view this term as -x times y. So as we do the product rule, we go through twice. The first time through, we take the derivative of the first term and we leave the second term alone. The derivative of -x, we bring down the negative sign, and the derivative of x is, well, it's dx dx. We're taking the derivative with respect to x, and that's just a 1. The first time through, we leave the second factor alone, and then we put a plus. Then we go through it again. The second time through, we leave the first function alone, so this is going to be -x, but because of the minus, I'm going to erase that and just put -x. And this time we take the derivative of the second factor, the second function. The derivative of y with respect to x is dy dx. So that was the product rule. Moving on to the last term, first we take the derivative of the outer function, so we get 2y. But then we multiply by the derivative of the inner function. This is the inner function, and the derivative of y with respect to x is dy dx. So this is what I mean. The most common mistake is for students to forget to multiply by dy dx. That's why I just want you to get into the habit of doing the chain rule on every term so you won't forget. And the derivative of a constant is just 0. So all of this is equal to 0. We need to get all of the terms that involve dy dx on the left side of the equation and everything else on the right side of the equation. So I'm going to leave these two terms where they are, but I'm going to move all of this to the other side of the equation by subtracting 2x and adding y. So now we have this. Because both terms on the left have a dy dx in it, dy dx is a common factor that can be factored out. Think about it as a GCF. So I'm going to pull out dy dx outside of parentheses, and that's going to leave behind -x plus 2y. Which equals -2x plus y. We need to get dy dx by itself, so I'm just going to divide both sides by -x plus 2y. So basically this is going to end up in the denominator. This is an expression for dy dx. We need to find the slope by evaluating dy dx at the point 2 comma negative 1. Don't go plugging in the 2 and the negative 1 willy-nilly. You need to show that you are evaluating. Show that you are plugging in using proper notation. And it looks like this. We do dy dx, and we put a vertical line, and then at the bottom, we put the point that we are about to plug in, 2 comma negative 1. Now you are free to plug in 2 for x and negative 1 for y. For a brief moment, we have this, but this is negative 4 minus 1, so that's negative 5. And this is negative 2 minus 2, which is negative 4. So the slope we were looking for is positive 5/4. Now that we've got a point and the slope, we can write the equation of the tangent line, which goes y minus y, so that's y minus negative 1, which is y plus 1, is equal to the slope, which is 5/4, times x minus x, so that's x minus 2. And that's it. This is the equation of this red line. Let's practice finding the second derivative, which is the derivative of the derivative. So we need to find dy dx and then take the derivative of that. This is the expression that represents the second derivative in Leibniz notation. Notice that the 2 in the numerator part is between the d and the y. That's because the way Leibniz notation works, if we're doing the derivative of some function f, it would be d dx of f of x, sort of like this. But often we call it y instead of f of x. So that's d dx of y, which we simply write as dy dx. We don't leave the y off to the side. We go ahead and put the y up next to the d. So that's the first derivative. The expression for the second derivative looks like this. So we are doing the second derivative of f, or the second derivative of y. So this is why the little 2 in the top part ends up between the d and the y. It's because we are doing the second derivative of just a regular y. If we put the 2 at the end, we'd be doing the first derivative of y squared, and that's not what we want. By the way, when we read the first derivative, we sort of read it, dy dx. I don't know of a way of directly reading this with the d and the 2 and the y and the d and the x squared. So we just look at this and say second derivative. So let's take the derivative of both sides of this equation, doing the chain rule on every term. So the derivative of the outer function is 2x, and then times the derivative of the inner function, which is just x, would be dx dx, because we are taking the derivative with respect to x. But of course that cancels out, and so you can just do that in your head. And then we move on to the next term. The derivative of the outer function is 2y. The inner function is the y. So we need to multiply by the derivative of that inner function with respect to x, so dy dx. The derivative of a constant is 0. We need to have any term involving dy dx on the left side of the equation. Everything else needs to be on the other side. So let's subtract 2x from both sides to sort of move this over there. To get dy dx by itself, we need to divide both sides by 2y. So we will have dy dx is equal to negative 2x over 2y. The 2's will cancel each other out, and we are left with dy dx is equal to negative x over y. So this is the first derivative. the second derivative will be the derivative of this. Let's be very intentional about how we handle this negative sign. I'm going to view it as being part of the numerator. To find the second derivative, we are taking the derivative of both sides of this equation. The derivative of dy dx is the second derivative. But on the right-hand side, we need to do the quotient rule, which says, sort of as a poem, low d high, less high d low. Draw the line, and down below, the bottom squared will go. So there's the bottom squared part. Now, how is that poem again in the numerator? It's low d high, less high d low. Low means the denominator. So low. And then d high means the derivative of the numerator. So if I do the derivative of the numerator, I'm going to temporarily just bring down that negative sign, but the derivative of x with respect to x is 1. It's dx dx, which is 1. When you multiply by a negative, don't leave it here on the right-hand side. It looks too much like subtraction, and students forget and mess up the problem. So whenever you multiply by a negative, put it in the front of the term. So I'm going to put this negative 1 like that. So that's low d high. Less means subtraction. So that's low d high less high d low. High is just writing down the numerator, which is negative x. Now we have this minus negative x, which makes a plus. Maybe I'll show that we sort of modified it. So this is plus because it's minus, and then it was a negative x. So we did low d high less high, and now it's time for d low. But the derivative of the denominator is dy dx. So this is an expression for the second derivative. However, we need to write it in terms of x and y. We can't leave dy dx like this. But we already know that dy dx is equal to negative x over y. So let's substitute negative x over y for dy dx. If this was a test, you could stop here. This is an expression for the second derivative in terms of x and y. But we need the good practice, so let's simplify a little bit. X times x is x squared, and we do have this minus sign, so we're going to have minus x squared over y. If this were a multiple choice question, the answer would not look like this. They don't leave a fraction inside of a fraction generally. It's not considered simplified. Resist the temptation to cancel out this y with one of these y's. You can never cancel out things that are connected by addition or subtraction. That's a major common mistake that we see. Instead, let's make like denominators by multiplying this term by y over y. This is sort of like y over 1. So this term is going to make negative y squared over y, and then we have like denominators here. Combining these two fractions over the common denominator gives us what you see here in the numerator. We can bring the y squared up and put it in the denominator. Quick side lesson, a over b divided by c is a over bc. See how the c hops up? Why is that so big? See why the c hops up and joins into the denominator. So when you divide a fraction by something, whatever you're dividing by just goes in the denominator. So on my next step, I'm going to have y cubed. You might see something like this as the answer on a multiple choice question. This question has a part 2 that you're likely to see on your unit test and or the AP exam. So follow closely. Kids struggle with this a little bit. We need to show that the second derivative is equal to negative 36 over y cubed. Well, this is the second derivative, and this doesn't really look like this. I mean, it's a good thing that we simplified as much as we did, because it definitely did not look like this at first. In our simplified form, we already have the y to the third power that's in the target. I'm noticing this negative sign here out in the front and a couple of negatives in the numerator. So let's factor out this negative so we can have this negative right here. Factoring the negative sign out of the numerator and putting it in the front gives us this. Can you see where they are getting the 36 from? Well, x squared plus y squared equals 36 was the original equation. So this is a fact. This is a substitution we can do. X squared plus y squared can be replaced with 36. And that's what we have here in the numerator, x squared plus y squared. So now we've shown that the second derivative is equivalent to negative 36 over y cubed. Here's an example that I borrowed from the College Board. If tangent y plus x cubed plus 9 is equal to 0, then what is the value of dy dx when y equals negative pi over 4? Let's see if we can make dy dx appear by taking the derivative of both sides of this equation. Every term we're going to do the chain rule. So tangent is the outer function. So the derivative of tangent is secant squared. So we have secant squared. But then the inner function is y. And because of the chain rule, we multiply by the derivative of the inner function, which is dy dx. We are obviously taking the derivative with respect to x. For the next term, the derivative of the outer function is 3x squared. The inner function is the x itself. If we were to multiply by the derivative of that inner function, it would be dx dx, which cancels out, so we're not going to write that. Of course, the derivative of a constant is 0. So we have this equal to 0. Let's get dy dx by itself. Begin by subtracting 3x squared from both sides. Next, divide both sides by secant squared y. So here's our expression for dy dx. Now we need to evaluate dy dx when y is equal to negative pi over 4. Do not simply plug in the negative pi over 4. You have to use proper notation. You have two choices. You can either use this notation to show that you are about to evaluate. You're about to plug in a value. You can put a vertical line, and then at the bottom you put y equals negative pi over 4, and then now you can plug in your negative pi over 4 for y. We're going to need x as well. I'm noticing that our expression for dy dx has x's and y's, and they only gave us a y to plug in, but we need x too. So how do we get the x value when you're given a y value? You plug the y value into the original equation and solve for x. So let's do that. This is the other notation for showing that you're about to plug something in. You can simply say at y equals negative pi over 4. Now it's okay to start plugging in this value. So we have the tangent of negative pi over 4 plus x cubed plus 9 is equal to 0. Hopefully you long ago memorized that the tangent of pi over 4 is 1. What about the tangent of negative pi over 4? Negative pi over 4 is in the fourth quadrant, where the slope of the terminal side, and thus the tangent function, is negative. So instead of positive 1, this will be negative 1. Combining like terms gives us this. Subtracting 8 from both sides, we have x cubed is equal to negative 8. Taking the cube root of both sides, we get x is equal to negative 2. So we have x and y now, negative 2 and negative pi over 4. Now we can evaluate dy dx at -2, negative pi over 4. Make sure to use proper notation like this. Substituting -2 for x and negative pi over 4 for y gives us this. In the numerator, -2 squared is 4 times -3 is -12. But what is the value of secant squared of negative pi over 4? Here's my thought process. We memorized long ago that the cosine of pi over 4 is 1 over radical 2. Or you might have learned it as radical 2 over 2, which is the same thing. Negative pi over 4 is in the fourth quadrant, where cosine is still positive. So the cosine of negative pi over 4 is also 1 over radical 2. Secant is the reciprocal of cosine. So the secant of negative pi over 4 will be the reciprocal of this, which is why I wrote it this way instead of radical 2 over 2, because when we do the reciprocal, it becomes a nice, simple radical 2. Secant squared negative pi over 4 will be radical 2 squared, which is just 2. So this becomes -6. Here's another problem I borrowed from the College Board. Pause the video and try to do this problem by yourself. Which of the following is true about the curve x squared minus xy plus y squared equals 3 at the point 2, 1? I'm going to leverage the fact that we had almost the same equation at the beginning of this lesson. We had a 7 instead of a 3, but when we found dy dx, the 7 became a 0 right away, and a 3 would also become a 0. So dy dx is not going to change. So we can use this expression for dy dx on the problem we are doing now. The options are all about the tangent line at the point 2, 1. So let's try to find the tangent line and see what happens. To find the equation of a tangent line, we need a point and the slope. So we have the point 2, 1. We just need to find the slope, which will come from the derivative. So let's evaluate the derivative at the point 2, 1 to find the slope. Let's practice using our proper notation. Dy dx at the point 2, 1. And now we are allowed to plug in 2 for x and 1 for y. We get this, which is -4 plus 1, that's -3, over 0. Aha! You can't divide by a 0. Dy dx is undefined. Assuming the point 2, 1 is on the curve, there will be a vertical tangent line at 2, 1 when dy dx is undefined. The only option that says dy dx does not exist is option D. So that is clearly the answer. Let's do one more College Board problem. Verify that for the relation y equals the natural log of 3x plus 4y, dy dx equals 3 over 3x plus 4y minus 4. To make the dy dx show up, we definitely need to take the derivative of both sides of this equation with respect to x. The derivative of y with respect to x is dy dx. We're going to need the chain rule for this one. Make sure you have memorized this rule. The derivative of natural log u is 1 over u, and then the chain rule, times the derivative of the inner function. In this case, the inner function, the u, is 3x plus 4y. So 1 over u is 1 over 3x plus 4y. That's the derivative of the outer function. Now we need to multiply by the derivative of the inner function. The derivative of 3x with respect to x is 3. And the derivative of 4y, bring down the constant 4, but the derivative of y is dy dx. Putting this expression in the numerator gives us this. Somehow I need to isolate the dy dx, which means I need to get both of these dy dx terms on one side of the equation with everything else on the other side. I think I need to split this apart. I'm going to use what I call the a plus b over c rule, which says I can rewrite an expression in this form as a over c plus b over c. So c, in this case, is the denominator, 3x plus 4y. And I'm looking at this as my a and this as my b. So I can take this one fraction and split it up into the sum of two fractions using the common denominator of 3x plus 4y. I take the first term and put it in the first fraction, and the second term goes in the numerator of the second fraction. All the dy dx's need to be on the left side of the equation. So I'm going to subtract this entire fraction to move it to the other side. The reason why we put the dy dx terms together on one side of the equation is so that we can factor out the dy dx as a common factor. So let's pull the dy dx outside of parentheses, and that's going to leave behind 1 from the first dy dx, and then minus the rest of this, 4 over 3x plus 4y. And then it's still equal the rest. Ultimately, we need to get dy dx by itself. But first, let's simplify what's inside the parentheses. Let's turn this into a single fraction. We need like denominators to combine these. It's easy to work with the number 1 because you can replace the number 1 with anything divided by itself. So we can just take the like denominator that we want and write it over itself because that's equivalent to 1. So now we can combine these fractions by taking 3x plus 4y minus 4 and putting that in the numerator. Now we can get dy dx by itself by multiplying by the reciprocal of this fraction on both sides of the equation. When we multiply by the reciprocal of this on this side, it cancels out. So really, this is just going to wind up over here, but it's going to be the reciprocal. Be careful, you cannot cancel these out because these are connected by subtraction, and you cannot cancel out things that are connected by addition or subtraction. However, these are connected by multiplication, so you can cancel these out. That leaves dy dx equals 3 over 3x plus 4y minus 4. And guess what? That's exactly what we were supposed to show. Hey guys, don't forget to like and subscribe, but also if you found this video helpful, there's a lot more where that came from. You can click the upper link, which will take you to the whole unit playlist, or you can click the lower link, which will take you to the next video in the playlist. See you there.